Yeah, I think it's recording. Sure, then I'll start. So, hi, good evening. Welcome, everyone. Um, today, we are going to have a little demo on some of the subjects that I teach for GATE CSE. And before we begin, I'll just introduce myself and give a couple of guidelines on how I like to take my lectures. So, I would really like it if you are very like if you participate when I'm teaching. Like when I ask questions, feel free to put it in the chat, feel free to unmute yourself and ask me questions, put me on the spot, ask me any difficult question that you encounter, while thinking whenever, like whatever current topic is going on. So I would really love that if you do. So on to my introduction. So my name is 𝗤𝗫𝗁 𝘂𝗫𝗁. I've done my MTech from IIT Bombay in the year 2022. I've passed out in year 2022. And I was GATE All India rank 53 in 2020 GATE CSE. After that, I've had some professional experience in Oracle India. I was a software developer there for 2.5 years, and then I've switched to teaching completely. And the primary subjects that I teach include C programming, data structures, algorithms, and I teach a couple of more subjects. But today we'll be talking about these three. So I won't go into much detail I won't go into in depth in any topic today. We'll just, we'll just browse through some of basics, some concepts which we should know. Okay. Anyways, we are going to cover everything when we start our regular classes, but these are some things, some fundamental concepts which we should know. Okay. And as for me personally, I used to face some issues when I was studying. So I like to, whenever I take a demo class or a basic concept class, I like to go through these topics. So we'll start. Okay, I'll write something on the screen. Can someone tell me what is this? X square plus 2y minus 3 is equal to 0. Feel free to put. What is this? Yes, yeah, it's a polynomial. Can I call it a mathematical equation? A more generalized version? Yeah, it's a polynomial. Yeah. So, okay, can anyone tell me any values of x and y for which this equation is satisfied? X square plus 2y minus 3 is equal to 0. Any values of x and y where this equation is getting satisfied? There will be more than one pair. You can answer any. Okay, 1, 1. Let's see. Is 1, 1 satisfying? Yeah, exactly. 1, 1 is satisfying. So if I give x and y the values 1, 1, it will satisfy the above equation. Now, the solution to this equation is not important here. What's important here is that what are x and y in this situation? Are x and y the values 1, 1? Are these two equivalent? Are these equivalent? Or is 1, 1 just one of the many values that x and y can take? Yes? Yeah, it can take other values. Exactly. So these 1, 1 is nothing but some data, and you are putting this data into some placeholder. These are nothing but placeholders. X and Y are just some placeholders which are there in the equation, and they're ready to, take some value so that the equation can be satisfied. So similarly, like we have in mathematics, similarly in computer science, we have data, right? Like when we have it, we have different types of data. Let's say X and Y are the placeholders in computer science. So X and Y here, we call them as, what do we call them as in computer science terms? These placeholders which can take some value, which can take some data, which can represent some data. What do we call such entities? Any ideas? In programming, in C programming, or in general in computer science? Exactly, variable. Very good, Ronak. So yes, In computer science terminology, we call them variables. And these variables can have different types of data. It can be it can be 10, 20, it can be some decimal value, it can be some letters, can be a symbol, comma. There are different types of data that can exist in computer science, and depending on the type of data, there are some predefined types which can store this data, and we must be aware of these. These are integers. This can be stored in float or let's say double data types, and these are your character data types. Now, each of these data types can be seen as a container. Okay? Like it's like a small container. Let's say this is an integer, this is a 2-byte container. Okay? Float, double, let's say these are 4-byte containers, and character, it is a 1 byte. So these all will be already predefined in your system. These are all predefined or primitive data types. Predefined or primitive data types. These are already defined in your system, and you can directly use them. Okay, you can directly use these data types to store the appropriate data. This is one thing. These are primitive data types. Others become user defined. Suppose these data types are not enough to achieve whatever we want to achieve, so we define our own data type. We take different instances from all of these and we just create our own data type. Can anyone tell me what do we use to create a user defined data type? Anything, any mechanism that we use? Yes. If I want to incorporate like multiple types of data into a one, let's say one big container, I want to place this small I want one integer, one float, and one character. What can I use for this? What do we generally use in programming? Exactly, we use a structure. Very good, Vignesh. So we use a structure. So let's say I'm not happy with all the primitive data types I want. So I create my new type. Let's say struct new type, which will contain an integer, a float, and a character. Correct. So I can create my own data type, and then I can also define some operations on it. And all of these things we'll see when we study it in much depth in C programming. Coming to the definition of data structure. Okay, we have primitive data types. We have user-defined data types. So is storage enough? Is storing a data enough? When we have some particular data, let's say I have an integer, I have a float, I have a character, and I store that data. Is it enough? Like, does data do us any good if it's just sitting there? If you have bought some expensive shoes, will it give you any use if you just keep it in your cupboard or in your shoebox? Yeah, it will use memory, but is it any use? Like, if you're not using it, if you're not doing anything with it, is it of any any significance to us? Unless and until we wear those shoes, it's of no use to us, right? We are not just showcasing it. Yeah, exactly. So here's where data structure comes into picture. So what is a data structure? What do you know? What is the definition of data structure that you know? Like whatever you have studied in your courses, in your colleges. Yes, anyone? You can unmute yourself if it's taking longer to type. I'm very I'm like I prefer verbal communication. I mean, it's totally your wish. I won't force it. It helps us to organize and gather data so that memory can be used efficiently. Yes, very good. Exactly on point. It is exactly correct what you're saying. Yeah, like we need an efficient mechanism to store, to organize data such that it can be efficiently used. Exactly. One more definition, which I like to go with, it is data structures are mathematical and logical model of organizing interrelated data. I know this definition is not very intuitive, like what is mathematical and what is logical, like what the hell, what is this? So let's take an example. Let's take a real world thing. Now, all of you, I'm hoping, are in colleges. So in your life, you must have, shifted like to a new home or shifted to a hostel room, or you must have done, you must have shifted to some other place to live. So consider, let's say this is your hostel room. The first time that you went to your college, this is your hostel room. And you bought all your stuff with you, right? Your computers, your books, everything that a student carries. Now, whatever you have here is your data, correct? You have your clothes, you have your books. When you enter into this room, there is a cupboard, okay, in which you can keep your clothes. There is a study table where you can put your books on. There's a chair where you can put yourself on. Okay? Oh, I'm very bad at drawing, so pardon me. Yeah. So all of these things that you see, your cupboard, your study table, let's say there's a shoe rack, which I don't think any hostel room has. You just put it under your bed, but let's assume um, it's a like a private college hostel room. So when you put your data into this, correct, you know that your clothes will go into the cupboard, your books will go on the shelf or on your table, your shoes go into the shoe rack. So all of these spaces that you see, these are predefined, correct? These are predefined storages, correct? Already someone has constructed these pieces for you so that you can put your data inside it. So when we come to the definition, when we say a mathematical model, this mathematical model is nothing but it stands for your predefined storage. This is predefined storage. So mathematical model will stand for predefined storage. So what does logical model mean? Now, when you put your expensive shoes in these racks, you won't just keep it there. You'll wear it to your annual functions, to your, to your dates and stuff. So you are basically using this. You're taking this data, and performing some operations on it. Correct? You're performing some operations on it. So this operation signifies the logical model. Operations. You're storing data in some predefined storage, and you are using that data. You're manipulating that data. You're using that data to achieve something. Okay, so mathematical and logical model of organizing interrelated data. Interrelated means homogeneous, similar type of data. Homogeneous, or let's say similar type of data. Okay. So this is in short the definition of it. Now first we'll look at the storage part of it. Okay? Depending on how you store this, how the data is stored, there is a classification. Okay, classification based on how the data is organized. How the data is organized. Okay, so there are two major classifications when we classify on basis of organization. First one is your linear data structures. Linear data structure. What are linear data structures? In a simple line, it says that data structures in which linear order is preserved. Linear order is preserved. What do you understand by this? What does a linear order mean? Does it click anything for you? Yes, anyone? Is this intuitive? What is linear order? Because the first time I saw linear order, I had no clue what it is. One dimensional, okay. Anything else? Not necessarily one dimensional. Are you sure about that? It's a good try, but I'll give you that. It's a good try. Linear order. Okay, I'll give you a small hint. Think about two things, okay? How the data is stored and how the data is accessed. These are the two things, and now you tell me what it can be, what a linear order can mean. Think about two things, how the data is stored and how the data is accessed. What should be linear in that case? Yes, I see new people typing. I'll wait. Yeah, I tend to do this. Okay, I tend to force you to participate. I don't care if it's via text, but I like, yes, exactly. Sequentially stored, yes, good. Sequentially stored, arrange sequentially, okay, good, good. Answers are coming in. Okay, you are slightly correct. So um I'll tell you what it is. When you say linear order, it means that you can access the data sequentially. Okay, but it is not necessary. It is not necessary to store data in continuous locations. Continuous memory location. It's not necessary in continuous memory locations. Okay. One more thing. To make it more intuitive, what I like to teach is that even if you don't remember any of this, what's the best way to remember the linear order is that whenever suppose I have a data structure here, okay? Let's say I have some data structure, okay? And there is a lot of data in it. If I am at some particular point in the data, okay? Let's say I am at some particular point in the data, and if I have an idea about where the next data is stored, then I can say that it is a linear data structure. Is it intuitive? Let me write it down first. At any random data in the data structure, if I have an idea, about the next part of the next data, the following data, I can say that it is a linear data structure. Okay, so anything is correct. You can directly say the linear order is preserved. You can say that I can access the data sequentially, but it is not necessary that I need to store them in continuous memory locations. And one more intuitive statement is that if I am at any particular data, I should have idea about the next data. I can say that that way linear order is preserved. So what could be different ways of preserving this linear order? Can someone tell me? There are two broad ways. One though we have on screen only. Okay? One is like first method is on screen. If you look carefully, how can I ensure that my data structure is linear? I don't want to take much of it. This is like a straightforward thing. How can I arrange sequentially? Okay, this is the previous answer. Look here, continuous memory location. Array stack queue are the type of data structures, correct? But if you, array stack queue all follow these thing where we store the data in continuous memory locations. So if I do one thing, let's say if I have some memory, okay, if I have some memory block, let's say these are my memory addresses 100, 102, 104, 106, and so on. And if I have, let's say I have to store 5 integers, the best way, the most easiest way to ensure that my that this is a linear, I'm storing it in a linear data structure, is that just store it in a continuous memory locations. Okay, so that way you can access them sequentially. Even if you're at any particular point, you can have you just need to increment by whatever the size of an integer, and then you can go to a next memory location. So one way to preserve linear order is that to store in continuous memory location. Store in continuous memory locations. What could be the other way? Suppose I don't want to store in continuous memory location. Take a first part of my data is at 100th memory location. Second part of my data is at 204. Third part of my data is at 506. How do I maintain linear order now? Is there any mechanism or is there anything that can help me maintain linear order? Among all the data structure that you know of, think about one particular data structure that uses this particular technique. What can I use if my data is not stored in continuous memory locations? Which mechanism will help me preserve the linear order? Pointer, exactly. Very good. So if I have pointer is nothing but, see, pointer is nothing but a variable. We will study pointer in much more depth when we study C programming. But for now, pointer is a variable. It's nothing. It's just a variable which stores addresses. Okay. So if I use pointer, I can store the addresses of the next part of data. Correct. The next data, whatever the next data is there, I can just store the address of that particular data along with the data that I'm storing. Okay. So for every particular, let's say this is my data D1, and with this I'll store the address here 204, so that whenever I am at this data here, this is D2 data, and it stores the address of next, and so on. So whenever I am at this data or any particular data, let's say we are here, I know that, okay, this is my data and the next data can be found at this location. Why? Because we are using a pointer to store it. And which data structure uses this mechanism? SSL, yes, singly linked list, exactly, linked list. So linked list, and here we can say arrays, stacks, queues. Stacks and queues can be actually they can be implemented using both of this. So I'll just put it arrays for now, and here linked list. Exactly, very good. So this way we can maintain. So this is basically a linear data structure. It's okay if you don't note now. It's not necessary to note. We'll again, we'll when we start our topics, when we'll go through all of these. Okay. So naturally, if first is linear data structure, other are non-linear data structures. Non-linear data structure. And as the definition would say, the linear order is not preserved. Linear order is not preserved. Not preserved. So you can access the data non-sequentially and store them. It's not necessary that you store them sequentially or you access them sequentially. What are some examples of non-linear data structures? A couple of them I'll note down. Trees, graphs, which we are going to see eventually. And one more is there, hash table. I'll just give a little illustration on how this non-linearity comes out to be. Are you aware of hashing? Are you aware of hash tables? Have you studied in your colleges? A little bit? Yes, exactly. Very good. So just a brief about it. Suppose we are implementing hash table using an array. Okay? These are my different memory location. What do? We get a key. Okay? We pass it through some hash function. Okay? This is a black box for now. Whenever we study, we'll look at it in much detail. We pass it through a hash function and we get some address. Okay? Let's say K1 is stored here. Then I get a key K2. Again, I pass it through hash function. It hashes, it computes the address for me. It computes the index for me, and I put it there. Similarly, I'll have a K3 and so on. Suppose I put K3 here. This is the index. So if you are at any data point, suppose in your hash table, if I am here, let's say I'm at K3 or I'm at K2, can I say do I have any certainty? Do I have some mechanism which will definitely tell me where K3 where K3 is stored? Can I say anything like this? Is there anything which will help me? I'm not using the hash function, obviously not using the hash function. I don't know what is the value of the key K3. So naturally, I will not be able to use the hash function. So if I'm at K2 at this point, is there any way to say for certain where the next key, let's say K3 is located? Does someone have any method? Open chaining? Okay, but in this particular scenario, that's even that's a bit controversial. We can't say like in open chaining as well. We'll see when we get there. We'll see how we cannot say. But in this particular example, because all the keys are hashed using a hash function, and whatever index we get for these keys, we store them there. So without knowing this key value, can I guess what would be the memory location for it? I need to know the value of K3, right? Only if I have K3, then I can pass it through hash function, and then I can say, okay, K3 is located here. But if I am at K2 and I don't have any other information, I cannot say. where K3 is located. So this is one way how the non-linearity comes into picture. When we study trees, when we study graphs, I'll explain in detail before we start any data structure. We discuss these things like, okay, this is non-linear or this is linear, how this is linear and how this is non-linear. So we are going to discuss all this. This is just a small illustration using hash table because it's thoda sa simpler. We don't need much additional info when looking at this. So these are broadly two categories in which we classify your data structure depending on how the data is organized in them. This became the mathematical, the storage part of it. Now, whenever we study it, we will study like any data structure we look at. First, we look at the storage part of it, how it's defined and everything, and then we go to the logical, which is the operations part of it. What are the can you tell me some commonly used operations that you might have encountered on which we perform on a data structure? Count, number of nodes in link, insertion, deletion, sorting. Exactly, these are. Is there something called as traversing? Yes, exactly. So first, so these will mostly be how sequence of operations will look at one by one whenever we see a data structure. First would be traversing. We'll visit. Traversing says that visiting each and every element at least and at most once. Now this is just a fancy way of writing exactly once. Okay, exactly once. We need to visiting every data in the data structure exactly once. Other, as Vignesh has already said, insertion. Insertion, as the name suggests, that we need to add an element into the data structure. Deletion, and let's first say insertion. Suppose I have a data structure. Okay, it is already full. Okay, there is a lot of data in it, and I'm saying it is already full. If I try to add one more data element into it, will I be able to do it? Can you add something? Can you add additional things in something which is exactly this type of situation where you cannot add anything into a data structure when it's already full? It's a error condition. Technically, we call it as overflow. And exactly the opposite of it will be the deletion. Suppose there is an empty data structure, and if you try to remove something from it, again it will result in an error. Sorry. Yeah, this technical term for this error is underflow. We cannot insert into already full DS and remove from a empty data structure. The last one which we'll look at in our DS course is searching, finding an element into a data structure. Now this searching, whenever you search for an element, output for searching will vary depending on what type of data structure you are studying or on what type of DS you are applying the search function. Let's say in case of an array, if you find an element, if the search is successful, so it will returns index of that particular data, returns the array index of that particular data if you find it. If you don't find it, if the search is unsuccessful, it will return whatever is the lower bound of that array -1. We'll look at it. What is lower bound? What is upper bound? We'll study all of these things. In data structure, arrays represented using lower bounds and upper bounds. So this is array. Suppose if it is a tree or a linked list where you are performing your search operation. In this case, if the search is successful, you will get the address of that node. Okay, because tree, linked list, all of these data structures are represented using this entity called as node. So in case of successful search, you get address of the node, and if the search is unsuccessful, you get it just returns null. So the output of searching function or search operation depends on what type of data structure you're performing the operation on. And the next two operations are sorting and merging. These two data structures, these two operations we will see in when we study algorithms. This will be covered because there are various methods to sort and to merge. And then, as the name suggests, sorting is arrange all the elements in one particular fashion, be it increasing or decreasing, and merging is combining two or more data structures of same type. Okay, so these are your classification based on, we saw the classification, we saw what common operations we'll see for each of the data structures. Now before going before even starting data structures, we need to have one more idea about one more thing, which is rate of growth, denoted by ROG here, rate of growth. And after that, we'll see complexity, rate of growth. What is rate of growth? Any idea about rate of growth? Does anyone know what rate of growth is? Complexity, okay. ठीक है, चलो. Let's say, okay, Ronak, let's say I ask you to go to market for me and buy me a laptop. Okay, I ask you to buy me a laptop, which costs around, let's say, 1.5 lakhs. Obviously, I'll be giving you the money. I won't ask you to buy from your own. And I also ask you to please bring me a Type-C charger along with it. Okay, which costs, let's say, around 150 rupees. So your total, what your total expense would be 150,150. Now, if anybody asks you, here, how much did you spend in the market today? What, like, how would you answer it? How would you answer if you bought these two things? Ronak, for you, like, if I ask you how much did you spend approximately, how much did you spend in the market today? And let's say you buy other couple of things, 10 rupees, 15 rupees, you buy some chocolates and stuff. What would you say? Approximately how much did you spend in the market? Exactly, you spent around 1.5 lakhs. You would approximate your expense, correct? You would approximate it. Because why would you approximate it? Because here, this particular cost is much more, it's much bigger to whatever your other expenses are. So this is a dominant term here. Okay, this is a dominant term with respect to this. Other things, like it's just like penny to dollar, something like that. So what rate of growth says is that rate of growth, the formal definition, it says that rate at which the running time increases as function of input. This is a formal definition. Let's look at it more clearly. Okay? Is the definition okay? Rate at which running time increases. So as you're increasing your input, with respect to that, how your running time is increasing, that is nothing but rate of growth. Okay? Rate of growth of input. Let's put it that way. How, like, rate of growth of the running time with respect to the input. Like with your increasing input size, how your total running time is behaving. Let's take an example here. Let's say I have a function f of n, which is n to the power 5 plus 2n square plus n plus 500. Okay, for n equal to 1, what would be the values that I have? 1 plus 2 plus 1 plus 500. Okay, so 500 is the bigger term here. Let's slowly increase our input size. N is nothing but an input here. Okay, let's slowly try to increase our input size. Let's say increase it to increase n to 2. So this becomes 2 to the power 5, which is 32. This becomes 4 into 8. This will be 2, and this will be 500. Still, 500 seems to be dominant, right? 500 still, it's not increasing, but it seems to be dominant as of now. So if I keep on increasing this value, if I keep on increasing my output to a large value, let's say, not to a large value, to greater values, let's say I'm keeping n equal to 10. 10 to the power 5 plus 2 into 100 is 200 plus 10 plus 500. Now, can you observe something here? Can you observe the growth of different terms here? Let's say these are terms A, B, C, D. Naturally, can you tell me which is the term which is growing at the fastest rate? A, B, C, D. Yes, exactly. A, as it's evident, A is increasing rapidly. This is not, the D is not increasing at all. Okay? So these are the different rates of growth for these different terms in this particular equation. So if I have to calculate the rate of growth of this function, if I want to calculate the rate of growth of this function, what can I say? Rate of growth of f of n is nothing but n to the power 5. I can, because why? Because this is the dominant term. With respect to this term, the others are not growing. Like the others are growing very like the growth in the other terms is very less significant. Correct? So this is how you would calculate rate of growth. You see the dominant term, and then whatever is the dominant term, that will be part of your rate of growth. We are going to practice this a lot when like in algorithms and data structures as well, but these are some things we should know. And different types of rates of growth include constant. Okay, what would be constant? Constant would mean there is no growth. Okay, with increasing input size, there is no growth. In this particular example, can you tell me among ABCD which of the particular term has a constant rate of growth? Which term has constant rate of growth, which is not changing? Exactly, D. It is not changing with increasing input size. No matter what input size you take, this 500 will remain constant. So D term, exactly. There is a linear, linear rate of growth. As you keep on increasing your input size, your running time increases linearly. So in this example again, which function is growing, which term is growing linearly? Linear rate of growth is exactly C, correct. So linear is C in this. There is a logarithmic rate of growth, logarithmic, which will denoted as log n. Then there is log linear, which is n log n. Then we have quadratic, which is n square, cubic, and so on. We have exponential, which is 2 to the power n, and factorial, and so on. So these are your increasing rates of growth. Now, coming to the complexity, let's park complexity for now. See, there is an input, and what are we doing on this input? One thing is that input size. Okay, how the input size increases. When the input size increases, what is the behavior? We already saw. This is governed by rate of growth. What is one more behavior of input? Is input size enough? Is the order in which the input is presented to us also important? Correct. Order in which input order. Is this also important to us or not? Or it won't matter however the input is presented, like our result will always be the same. Is that the case? Or depending on how the input is presented to us, we might get different results. Exactly. Order is important, correct. So depending on this order, whenever we analyze an algorithm or whenever we analyze operation or a process, input order is also important. So when you analysis of any algorithm or process, the input order comes into picture. Okay? And what are different types of analysis that we have? We have a worst case analysis, we have a best case analysis, and we have a average case analysis. Okay? Best case, average case, and worst case. What worst case says is that, what worst case defines is that it defines the input, it defines input order or input, it defines input for which the algo or the process or the operation, the process, the algo or the operation takes longest time to complete, takes longest to complete. Takes longest to complete. Depending on the input order, the worst case would be which such an input for which the any particular operation takes the longest to complete. So intuitively, best case would be fastest to complete. Fastest to complete. Best case will define an input for which the algorithm will take fastest to complete. And average case, it basically gives us a prediction. gives us prediction on running time of algorithm. Okay, it just gives us a prediction on running time. And how does it gives us a prediction? It assumes a random input. That way, it gives us a prediction on running time. Now, for any sorry, so now when we combine all this, we get closer to complexity. Okay, is this still enough? Is this still enough to define complexity? We have rate of growth, we have worst case, best case, average case analysis. Now I want to represent a complexity. Like first of all, what is the complexity? Even before going to that, is this okay? Input has two. We can say that input has two characteristics. One is the size, which can vary, and it is governed by rate of growth. Other is input order, which can be analyzed using these three different cases, which are your worst case, best case, and average case. Is this clear to all of you? Is there any doubt still now? Does this seem fine? Okay, ठीक है. So when we come to complexity, what complexity says is that the definition says that it is how efficiently your algorithm, utilizes system resources like time, space, etc. Now, if I want to, whenever we want to present something, we or quantify, not say quantify is the wrong word to use it. Whenever we want to represent something, I would need some notation, to represent this rate of growth. Yeah, along with your what do you say, whichever case you are analyzing at the point, you would need some notation to represent this complexity. So let me write it down. How efficiently the, the system resources are used. System resources are utilized. System resources like time, space. Okay. So to represent this complexity, we use a notation called as asymptotic notation. This will study in much more detail, but we'll just broadly, briefly go through the important notations, because these are some things we require when we study data structures. So asymptotic notation, why is it called as asymptotic? We'll see all that when we formally study it. So for each of the cases that we analyze, let's say this worst case, best case, or average case, whatever cases we analyze, for each of these cases, we will find bounds for this, like a lower bound and upper bound for each of these cases. And that's where this asymptotic notation will help us. So first asymptotic notation that we are saying is big O notation. Big O notation. Okay, let's say, what does this big O give us? Take it. Let's say I have two functions, okay? F of n, and I write it as and g of n, and I write it as f of n is equal to O of g of n. This is how you would pronounce it. F of n is O of g of n. Now, when I write this particular statement, what does this mean? This means that for sufficiently larger values of n, for larger values of n, g of n is the upper bound of f of n, which it means that for sufficiently larger values of n, g of n will always be greater than or equal to f of n. F of n can never be greater than g of n. This is what this is what is implied by this statement. Okay, that's the reason it's also called as this big O notation. Also signifies tight upper bound. Now, again, it's still not very, just this notation is not very, even with the definition, it doesn't paint the picture here. So let me write it a little mathematically, what this particular statements means? This statement means that f of n is less than or equal to, when I write this statement, I want to say that there exists some constant c which is greater than 0 and another constant, let's say k, which is greater than 0, greater than or equal to 0, such that f of n is less than or equal to c into g of n for all n greater than or equal to k. If I try to draw a graph for this particular expression, look at this expression carefully. I'll wait for a second here. This notation, f of n is O of g of n, says that there exist two constants, which is c and k, such that f of n is less than or equal to some constant multiplied by g of n for all values of n equal to n greater than or equal to k. Let's say this is my f of n function. Okay, so this is my f of n function, and here, where did it go? Okay, let's say this is my g of n function. Okay, this is some constant c into g of n. This point, okay, this is my point k. Now before this k, let's say n0 equal to k, this initial point. Now before this k, we don't care. We don't care how the function is behaving. Okay, how the two functions are behaving, how this c into g of n and f of n are behaving. We don't care about that. But at this k and after this k, this particular inequality should be satisfied. If this inequality is satisfied, if we have a valid k and a valid constant, we say that f of n is O of g of n. Look at the definition, and like I'll stay at this slide for a couple of minutes, like for a minute. Look at this. If you're feeling comfortable, let me know in the chat. If you're not feeling comfortable with it, again let me know in the chat. We'll see it. Same thing we'll see it with an example as well. Is the definition, because there are a lot of terms involved, so that's the reason I'll stay at this particular slide for a minute. Look at this. There are a couple of things we discuss. Big O notation. It is also which represents a tight upper bound. We write it as f of n is equal to O of g of n. When we write such a statement, it means that for larger values of n, g of n is the upper bound. It is basically bounding this function f of n. This is, see, in this particular range, this f of n will never be greater than some constant into g of n. This constants, it's just, it doesn't affect your whatever your graph would be. It would just scale your graph by some value, right? Constant don't affect the fundamental shape of the graph, correct? So whenever you multiply a constant with any function, it will just elevate that graph. So that's the reason we are not concerned about the constant for now. Is this definition, does this definition feel fine for big O notation? We'll see a couple of examples which will make it more clear, which will make it more intuitive. Sorry. If anyone has a difficulty understanding, please let me know in the chat. Again, this all will be discussed much more formally when we study algorithms, but this part should be, understandable. Definition is clear, but where is it used? Yeah, sure. Yeah, we'll look. It has plenty of application. Whenever we so one of the application is whenever you analyze an algorithm. Whenever we, let's say you have an array. What is the time complexity for insertion? That's nothing but an application of this notation, right? So let's look at a example. Okay? Let me give you an example. Let's say I have f of n as n square and g of n as 2 to the power n, and I want to check whether f of n is O of g of n. I need to check this. Does this hold or does it not hold? So because this is the first example, let me go slowly. we'll just take some value. We'll start with the value of n, and we'll slowly keep on increasing. And let's see the behavior of how these values, how these functions are behaving. So when n is equal to 1, f of n is 1, g of n is 2. For n equal to 2, I have this as 4. Again, this is 4. So now earlier f of n was less. Now they both have become equal. So for the value 3, this becomes 9 and this becomes 8. Now f of n is growing. For n, for the value 4, this f of n comes out to be 16, and again g of n is also 16. Again they got equal. Okay, no worries. Let's carry on. For the value 5, this becomes 25 and this becomes 32. For n equal to 6, this becomes 6 square is 36 and 2 to the power 6 is 64, and so on. So can you guess a pattern from this? If I keep on increasing, what's your guess? What would grow more? Which function is growing faster here? 2 to the power 10 is 1024. Can you see this? Slowly, the g of n has started increasing rapidly with respect to like compared to, yes, exactly, compared to f of n, g of n is growing much faster. So if I try to draw a graph for these two particular functions, so let's say this is my f of n. I'm just drawing a rough graph. We started with the value 1. We started with the value 1 where this was f of n. Take care. So initially g of n is bigger, then they become equal. So, yeah, then they become equal. Then skip after that f of n is bigger, then they again become equal, and then I think g of n is, it becomes equal 2 times, right? And 4 and 16. Yeah. So after that g of n keeps on growing with respect to f of n. Okay. So can I write that after this value, after n equal to 4, after this value, this is n equal to 4, so after this value, n is greater than or equal to 4, can I say that f of n is always less than or equal to g of n? Can I write this statement? F of n is less than or equal to g of n for all the n which are greater than or equal to 4. Is this a valid statement? Yes. Is this valid or is it not? The graph is in front of you, the values are in front of you. Yes, it is valid. So can you tell me the constants here, k and c? What would be k and what would be c? K, so I have already written, k is 4. This is nothing but 4k. And what would be the value of c? What is the constant c here? Would it make any difference if I write 1 into g of n? Would it be all right if I write 1 into g of n? It's one and the same thing, right? So if you look at our definition, this definition, I'll write this once more on the next slide. What's the definition of big O notation? It is nothing but f of n is less than or equal to c into g of n for all n which are greater than or equal to k. We have a valid value of k, we have a valid value of c. So can I write f of n is equal to O of g of n? Yes, I can write it because it is following my inequality. Correct? Any doubts? Is it more clear now? We will look at one more example. Okay. Okay. So let's see one more example. Yeah. Let's say I have a function f of n is 100n plus 5. 100n plus 5. And I'm okay. 100n plus 5. Can you tell me the upper bound for this? Whenever we say tell me the upper bound for this function, basically I'm asking you for the big O notation. Okay? Can you tell me what would be the upper bound for this function? 100n. Okay. Okay. See, whenever we write notations, okay, whenever we write big O notations or whenever we calculate bounds, we tend to generally ignore the constants. So if you're saying 100n, you can ignore the 100 here. Okay, because when you will be writing some expression in this particular notation, right? When you're writing this notation, you can ignore the constants. That's the reason we say bound, right? Because we want to ignore those constants which are in the expression. So there are multiple ways to do it. Yes, you're right. It will be O of n, but how? Okay, so we need to find. I need to find something. If you're saying that this f of n is big O notation of n, we need to see that it is following our inequality. Okay, so let's try it. Can I write 100 100 n plus 5 is less than is just a second. Hundred n plus 5 is less than or equal to 100 n plus 5. Can I write this? No, same terms on the both side. Is the inequality still valid? Is the inequality still valid? Here, a is less than or equal to a. Yes, it's a valid inequality. Correct. What if I multiply n here? Okay, is it still valid? Yes, is if n equal to 1. Even if n is, see, if n is 1 or greater than or equal to 1, n can have a bigger value. So it will still hold. Correct, because n by default, when we look at complexities, we don't care about the lower values, right? We will look at higher values. So yes, I can write this inequality. So 100 n plus 5 is less than or equal to 105 n. Can you see? Can you see this inequality is matching our big O notation? F of n is less than or equal to some constant into g of n for all n greater than or equal to k. Is this fitting the inequality? If it is fitting the inequality, what is the value of c here? What is the value of constant c? The constant c. The f of n, so we know f of n as it is written on the left hand side. This is your f of n given in the question. This is your constant c, which is 105, and g of n is nothing but this n. So c is 105. Now, do I have a k? How do you find k? You just do one thing. Once you find out the value of c, you just substitute it in the equation. So 100 n plus 5, and at that particular k, okay, as we have seen here in this graph, at that particular k, these two expressions will be equal. So you just apply the equality there. So when I keep the value of c equal to 105, I can just equate it 105 n. What is the value of n here now? If I calculate this, it comes out to be 1. So this k is nothing but 1 here. Okay, for all n greater than or equal to 1. So k is 1 here. Is this okay? How we calculated this, how we found this out? Yes, someone? There are multiple ways. This is just one of the ways that I'm this is not something that we will follow. Okay, that um, this is just for explaining how you can find out. Okay, this is not something. All of these things we are going to generalize when we study complexities, when we study asymptotic notation more formally. This is just to make it more intuitive, how to, how we can go about, because we need to see what we have studied till now. We have just studied this notation, this particular inequality. This is all that we know about this. So what I'm trying to do is that I'm just trying to put this particular function in that inequality so that I get a constant c and I get a what do you say a constant k. That's all we are trying to do here. So is this okay how we are calculating C, how we are calculating K? Yes, ठीक है चलो. So now is this unique? Are the value of C and K unique? What does your intuition say? Should this be unique? Because we are just, see, if you see, what did we do? We just did some hit and trial, correct? This thing here, I just wrote something which I knew for sure would be correct. This 5n, it's not necessary that it can be anything here, correct? So it could have been 106n, it could have been 110n. I could have taken any number. The inequality still would have hold, correct? Yes or no? If I would have taken, let's say in the second case, instead of that, I can also write 100n plus 5 is less than or equal to 110n. I could have also written this, right? Yes or no? I can still write this. If this is also correct. So in this case, my C becomes 110. And to find K, I just need to equate it. So I can just equate it 100n plus 5 equal to 110. 110. And in that case, my n would come out to be 0.5. Okay? So my K would become 0.5. So these constants are not unique. There is no uniqueness in this. Okay? Because why is it not important to us? Because at the end of the day, we are calculating a upper bound. Okay? We need to match these. We need to match this inequality which with our big O notation wala inequality. And when you actually, you find this inequality, you get a constant. You just ignore that constant when you are writing. Whenever you are writing asymptotic notation, what do we write? F of n is equal to O of n. Correct? We are not writing 105 or we are not writing 110. We just ignore those constants. So to prove if the notation holds or not, the constants are not important. If you choose any random value of C, your value of K will change accordingly. If the notation is holding, if the notation holds, no matter which constant you take, the values will keep on changing. Okay? Because when we match that inequality, we ignore those constants. We just need the function. We don't need the constants. So if you assume any constant, you will just get it. If you assume any value of C, you will just get a corresponding value of K. If you assume some other value of C, you will get some other value of K. Okay? At the end of the day, again, what do constant do? They just scale your graph. They don't affect the shape of your graphs, right? Here in the graph, they will not affect the shapes. They will just scale them up or down. Correct? So that's the reason this constant don't matter here. Whenever we are trying to prove any particular upper bound, or we are trying to find upper bound for something, there can be multiple methods to do that. Okay? Is this all right? The constant don't matter when you try to what do you say, when you try to find the complexities. And we are going to generalize all this. This is like a polynomial term. There's a generalization for polynomials, and we'll see all of them. We are just looking at how, if we don't know any of that, how to, if I don't know that generalization rule, how can I, how can I prove this particular thing? If I tell you, assuming this is all right, I'll ask you one more question. Let's say f of n is n factorial and g of n is n to the power n. Can I say that, can I say f of n is O of g of n? Can I say? Yes or no? Calculate. This is a question for you. Can I say that f of n is O of g of n? Okay, Vignesh is saying I can say that. Can you help me out? How, how would, is it just that something that you know, or something that you can, it will be a single constant line. Okay, ठीक है. चलो, let's, okay, you're typing something more, type. Can I write, what is n factorial? At the end of the day, let's see, what is n factorial? N factorial is nothing but n into n minus 1 into n minus 2 and so on till 3 to 1. 3 to 1. Can I write will this inequality be valid if I write n factorial is less than or equal to n? Now I replace all of these terms with the bigger number n, n times n. Can I write this? Yes or no? Can I write this? N factorial is less than or equal to all of these terms n minus 1, n minus 2. I replace all of this with n. Yes, exactly. I can say that. So what I'm doing here is that n factorial is less than or equal to how many times am I multiplying this n? How many times am I multiplying? N is getting multiplied n times. So that would become n to the power n. Can you see it fitting our big O notation wala inequality where the constant is 1 and we can for this constant we can find some k as well. Can you see this fitting that particular inequality for our big O notation where f of n, O of g of n, when we write this, the inequality, yes, exactly, it is matching that inequality. The inequality says that f of n is less than or equal to some constant into g of n for all k. Okay, so the constant here is c, and accordingly you can find what do you say? You can find the k for this. So I can write n factorial is nothing but O of g of n. The constant don't matter. We ignore constant after, once we get the inequality, once we get a valid inequality, we tend to ignore the constant because we don't care for the constant. It won't appear inside your, it doesn't appear inside your notation. Here we'll just write n to the power n. We are not writing any notations with it. Okay? I'll take one more example. Okay? One last example. I'll take a polynomial itself. Let's say f of n is n square plus n plus 1. Now this is totally for you. I'll wait for a couple of minutes. Let's take this as a last question. There are more asymptotic notations, but we'll study them more formally. The time is also almost up. So this just one last question for you. Is f of n O of n square? Yes or no? Is this O of n square? Is n square bounding this function? Yes, okay. ठीक है. Yes, I need more answers for this because this is the last question. I need more answers. Ronak and Vignesh are saying yes, this is bounded. We'll see that this is for polynomials. That's a rule which will make it pretty straightforward. But just because this is like the first time we are seeing this. Okay, let me. Yeah, do I have any more answers? Are you trying? Because this is not how we would do it. Okay, this is not how we would do it. This is just for an understanding for now. Okay, chalo, let me take it. Can I write n square is less than or equal to n square? Again, the same thing. A is less than or equal to b always holds. If I add n square plus n on this side and n square plus n square on this side, is this inequality valid? Because this is a smaller term and this is a bigger term. Will this hold? Yes? Okay. Similarly, now because see, why are we doing this? Because I want to recreate my f of n function. So let me add n square plus n plus 1. Now I am adding a constant on left hand side and on the right hand side I'm again adding the n square term. Okay, so essentially what I'm getting here is that this is nothing but my f of n, which is less than or equal to 3 into n square, correct? And if you look at it carefully, it again matches our big O notation wala inequality where c is 3 and I think k, can someone tell me what would be k? What would be k? Just put the value here, n square plus n plus 1 is equal to c is 3 n square. You just need to solve this equation. I think it comes out to be, I think one solution for this would be 1. Yeah, I think greater than or equal to 1 should be, k should be equal to 1. So again, this matches our inequality, k. So yes, I'm getting my inequality. I can write that n square plus n plus 1 is equal to O of n square. I'll just ignore the constant 3. I can write this. So this is one way of proving it. So the generalized thing is basically whichever is the highest power of your polynomial, that will be basically the upper bound, and that will also be a lower bound, which we'll study later on. But this is how you would find out the upper bounds. And there are much more sophisticated ways to solve these particular problems. This is just the intro part, so it's better to see it this way, and then you can jump to the more straightforward ones. So I think this is a safe point to stop for today, because anyways we are going to study these different notations in our regular classes. So I hope this was okay. Don't worry if you don't get it much in the very first viewing, because we are not in the regular class. We would spend much more time on these. We would take much more questions. This is just because it's a demo class. I didn't want to overburden with much heavier stuff. So I guess it's good enough point to stop here. We'll discuss all of this again. Yeah, I hope you had a good time. I'll share my screen. Okay. I just have a
Guys, any doubt? Thank you, sir.
Thank you. Yeah, I have a couple of questions. So, I mean, just regular questions. Like, are you have any of you attempted GATE before, or is it the first time that you would be attempting? Like, what's the consensus on this? First time, okay. So I think most of you would be in your third year, in your third year college, like third year of your bachelor's degree. Like second year, yeah, very good. It's good to get a head-on start then. Second year is a good point to start. I mean, I realized it very late, like almost half of my third year had passed by that time. So it's very good that you're aware of this. Yeah, good. Okay, chalo, then we'll accordingly carry on with our courses. So first we start with data structures, then programming, and then we at last we do algorithms. So we'll take much more questions. We'll solve many PYQs in our regular lectures. Yeah, I guess that's it from my side. I'll see you. Good night. If you have any doubts, please do ask. I'm here. Or if you have any other questions, you can ask me about GATE or in general about anything. Thank you. Thank you. Okay, Dinesh sir, I think if there are no more questions, I'll end the call. Is it fine? Dinesh sir, are you there? Okay, I guess he left. Okay, chalo, I think Dinesh sir is not here. I'll end the call. I'll see you soon. Bye-bye.